Hi, everyone. Thank you so much for coming to our talk. We're very excited to be back here at NDC Oslo and hope you've had a good first day at the conference. OK, so this talk is about AI, and specifically large language models. And we will share a practical perspective to how you can use LLMs, but we will also dive into some technical details into how our system is created. My name is Mathilde Ørstavik. I work as the head of AI at Norkart. I have a master's from NTNU in Trondheim, and I've been working at Norkart now for 7 years, mostly as a software developer. And I've always been very interested in how we can use AI in our products, and especially together with geospatial data. And eventually, I got the opportunity to lead a designated AI team.
My name is Malte. I have a master's in artificial intelligence from NTNU, and I've been working as a consultant for 6 years on various machine learning projects for Vy and Entur and Oslo kommune. And then a year ago, I had the pleasure of joining the AI team at Norkart.
There are a few more people in our team with different backgrounds and different specialities, and we're also very lucky to have Henrik in our team, who's actually working on his PhD in natural language processing. So we'll come back to specifics about his work a little bit later in the talk. So our aim in the AI team at Norkart is to figure out how we can use AI to both improve our products, but also improve the way that we work. And since we are a small team, it's very important for us to try to share or spread the AI knowledge across our company. And one of the ways we do this is that we invite different teams to join us for 2 days hackathons, where we choose some topic and let people get some hands-on experience with coding with AI system. So I thought we would share some few examples of results from these hackathons. So the first one is our own AI code reviewer. So this lives in a pipeline. It reads the Git diff on a pull request and gives a summary to what the changes in the pull requests are, and also suggests some possible issues. So this has been running for about a month now, and I think one thing that we can say is that the LLM is better at giving good descriptions of what the changes in the pull requests are. We tend to be a little bit short when we write our description, and some of the issues are actual issues that we do need to address. So it works pretty well. Another example of results from a hackathon is a chatbot we call Nora, Norkart AI. And she can reply to questions about things in Norkart, questions about our products, our tech stack, and things like that. So this is for internal use. And a third example is an extension that we made for GitHub Copilot. So you can actually make extensions to the GitHub Copilot extension in VS Code. So this is in preview for Microsoft. But we tested it, and we were able to add extra functionality specifically to Norkart so that we can use the GitHub Copilot chat and ask Norkart-specific questions, questions that are not necessarily related to the workspace that you're in. Also very useful. And then some examples of AI in our products. We have a route planner that we use in several of our systems. And we also work a lot with image analysis, and specifically detecting objects in aerial images. So we have models that can detect buildings. We have another model that can detect roads, but also swimming pools, terraces, and things like that. And what we have created is an application for the municipalities to go through the results and see what the AI has detected that isn't already in the map, so that they can, for example, detect illegal buildings. But the topic for this talk is about building services and specifically building permits. So first, we're going to talk a little bit about the current situation and building permits in Norwegian, byggetillatelse, just so everyone is on board. So first, we're going to talk a little about the current situation. And then we will talk about Planprat, which is our LLM system that tries to make this process of applying for a building permit a little bit easier. And we will talk about evaluation, how we can evaluate an LLM system, and finally talk a little bit about different models. So before I continue, just a small disclaimer. We are going to be talking about Norwegian text and Norwegian text analysis. And therefore, there will be Norwegian text on the slides. But we will try to translate everything that you need to understand. That there's also some subtitles on some of the slides, so we hope this will be OK for you guys. OK, so Norwegian municipalities, they receive around 90,000 building applications every year. They have limited resources and are under a significant work pressure. People expect quick responses to their building applications and also questions around how to fill them out. And all of this creates frustration at many levels. In fact, several surveys indicate that planning and building services have the lowest level of satisfaction among all municipal services. So applying for a building permit is really difficult. It's difficult both for the applicant, but also for the municipality. But why is it like this? OK, so a question, if I can manage to see you guys. Who here have applied for a building permit in Norway before? Quite a few of you. OK. So who here enjoyed the process and thought it was easy and OK? Anyone? I don't see any hands. OK, so for those of you who have not gone through this process, I'll try to explain how it could look like. So this is Permit Penny. And Permit Penny, she has this idea of a garage that she would really like to build on her property. So she goes to her computer and she starts looking online. Can I build a garage on my property? She soon figures out that the answer is, well, it depends. It depends on what size she wants to build, the distance to coastline, distance to property border, distance to avalanche risk, distance to railway. Does she want a loft on her garage? Are there existing buildings? How many on her property? What is the distance to different roads? And so on. So there are lots of rules and lots of things she needs to figure out. And all of these rules are what we can call national rules. They are the same across all of Norway. But there's still a lot to figure out. But it doesn't stop there. She soon realizes that there are a different set of rules, the so-called local rules. And the local rules are different for every municipality, but not just for the municipality, but also different for every property within that municipality. So she needs to figure out what zone she's in. Is there a building boundary on her property? What is the permitted utilization? Is there a maximum height limit? Are there rules for how the exterior should look like? And now she starts getting really frustrated. She has no idea what a building boundary is. She doesn't know how to figure out what the permitted utilization is and how to calculate it. It's just really overwhelming, and it's all foreign to her. So at this point, she has 4 options. She can choose to pay someone to help her. There are a lot of companies that can apply for a building permit on your behalf. She can choose to build illegally and hope that her municipality doesn't buy the AI service from Norkart that can detect illegal buildings. She can give up, or she can try her best. So Penny goes for the 4th option. So she starts digging into these local rules and tries to figure out what rules apply to her and her property. So what are these local rules? Local rules are called zonal plans, in Norwegian arealplaner or reguleringsplaner. And they are legally binding documents that provides rules for how land within an area can be used and what types of construction may be permitted. And the zonal plans consist of 2 parts. The first one is a text document, and the second one is a map. The text document is often written by lawyers and can be long, maybe around 100 pages. And there's not just one zonal plan for your property. There are usually several. So you have the municipal master plan, which covers the entire municipality. But then you also have zonal plans, detailed zonal plans, and also other types of zonal plans that I haven't added here. But there can be many different zonal plans for your property, and you need to look at each and every one of them. And the fact is that Norwegian municipalities are drowning in old zonal plans. So new zonal plans are added all the time, but they don't want to delete the old ones in case there are some rules and regulations that they still want to keep. So the number of zonal plans just keep increasing, and it gets more and more complex. But Penny is persistent. She has gone through all the rules. It took her weeks, but now she has finally completed her building application and sent it into the municipality. And she's quite confident that she will get her building permit. So now she just has to wait for the municipality to look through her application. That also takes a few weeks, but she finally gets a reply. She's super excited. She opens her email, but this is her response. Her application is rejected. She doesn't get her building permit. Because on page 124, in one of the zonal plans, there was a regulation that she hadn't realized applied to her that actually said that she wasn't allowed to build at all. So this is, of course, a made-up story, but in fact, 40% of all applications contain incorrect information or are incomplete. And a lot of this is related to the zonal plans and people not understanding how the zonal plans apply to them. So the zonal plans, they contain intricate words and expressions. It's a lot of information to go through, and the rules are chaotic and unclear.
Thank you. So how can we make it easier to understand these zonal plans? And the answer, all of you know the answer already. It is, of course, language models. Language models are the most hype of all the hype right now. It's where everything is happening. So let's try to explain a little bit about it. So actually, what most people don't know is that language models, one of the foundations for them is this theorem based on Barron from '93. And it's about if you take the integral of the gradient of f, then you can write f of x minus f of 0 to something like this. Oh, no, the sound doesn't work. No. Can we see how we can fix that? Or we're not going to fix that. We're not going to fix that, are we?
Try and go back.
We can try to go back. Maybe the technical people know something that we don't know. There we go. There we go. Okay. Pretend that this didn't happen. So, oh no, what just happened? Who is this?
Wait a second. This is Planprat speaking.
Planprat? But you're not even unveiled yet. What can I do for you, Planprat?
Do you really think people want to learn about this? Cut to the chase, bro. Come on.
Okay, okay. Well, relax, relax. You almost sound a little bit like Mathilde. But, yeah, I'll cut to the chase, no worries. So we're not going to go into the intricacies of the math here. We're just going to go through some few words that you need to know in order to follow this presentation. The first one is an LLM, and it stands for a large language model. Furthermore, we have prompt and prompt engineering. So when you work with a large language model, you can think of it as just something that takes text in and you get some text out. And the text in is called the prompt. And what you can do is that you can alter this prompt in order to manipulate the output from the LLM. So you can give an instruction such as keep it short, and the LLM is going to answer more concise. And this is what's called prompt engineering. Then we have tokens and embeddings. So when you work with large language models, these models, they don't understand words. They don't just work with numbers. So you have to somehow translate from words into numbers. And one way you can do that is by creating a unique ID for a given word. And this is called tokenizing. So let's say we want to tokenize king and queen. You can just give them two random values. The problems with this is that now we're losing all of the semantic meaning behind these words. And in order to combat that, you can try to make something called the embeddings. And the embeddings is just a list of numbers or vectors of numbers that represent one part of a text. So an embedding for king could look something like these 5 numbers, and the embedding for queen could look like the other one. And you can notice here that the 3 first numbers in these vectors, they're the same. And that's because king and queen are quite similar in the semantic meaning, because they're both royal. Another way of showing this is on a 2D plot. So you can see here that king and queen should be somewhat relatively close to each other, in the same way that, for instance, a man and a woman should be close on a separate part of the plot. But what's also more fascinating is that the distance from man to woman and king to queen is probably going to be around the same, because we have managed to capture some of the semantic meaning behind these words. And this doesn't stop at words. This also continues into sentences or even whole paragraphs. So you can make embeddings of paragraphs, and you can find paragraphs that are more similar to each other. And the last we have to cover here is something called context. So remember this conversation we just had with the AI? If you want to answer or ask it another question, such as how did you calculate that, you're now referring to something that happens earlier in the conversation. So you have to paste the whole chat history in. And this is what's called the context. And in this case, the context is just the chat history, but you can kind of give the language models anything or any relevant information that you think it should know about. So now that we know everything about large language models, what happens if we ask, for instance, ChatGPT if I can build a garage on my property? Well, ChatGPT is going to answer that building a garage on a property depends on several factors, including local zonal regulations and so on and so on. And that is, of course, because it's missing all the information to zonal plans. It's missing information about the geospatial information, such as the property information and where the property is situated and what is currently on the property. And it also doesn't not have any knowledge about the zonal plans expressions and intricacies. Yes.
So, challenge number 1. How can we give access to the zonal plans? So first of all, we as developers need access to the zonal plans. And at Norkart, we already have access to them, because a lot of the municipalities are customers of us, and we actually provide the system where they manage their zonal plans. So that's solved. So the next one is, how can we give the zonal plans to an LLM? So the first obvious one would be to just copy the entire plan. Just give the full text to the model. So this would mean that we would give it a lot of information, around maybe 300 pages, which again would be expensive, because you pay per token that the model is processing. And you would also give it a lot of information that could be misleading, because these documents contain so much text and regulations for an entire municipality, but you usually have one question related to a specific topic for a specific area. So this is where the RAG architecture comes into play. RAG stands for Retrieval Augmented Generation, and is very useful when you have a question that you need answered based on some documents. So the first step in a RAG architecture is the retrieval step. And the retrieval step can be done with an AI search. So I'll try to explain a little bit what it is. So the first step to create an AI search is to first take your documents and split it into chunks of text. So this is a part of the pre-processing that Malte will talk a little bit more about later, how the pre-processing actually works. But for now, just think of it as taking your documents and creating chunks of text. The chunks of text are then added to an embedding model. And the embedding model places the chunks of text in the embedding space based on their relevance. So if two chunks are similar to each other, it will be close to each other in the embedding space. If they're different, they will be further apart, like the king and queen example. The embeddings are then saved into a vector database, which allows us to perform a search. So we take the question, and we use this question to search for chunks of text that are relevant for that question. And the chunks of text that the search retrieves will most likely be the part of the text that you need to read in order to answer that question. So these chunks of text are then added to the prompt, together with the question, but we also need a system prompt. And the system prompt tells the system how it should solve its main task. The entire prompt is then added to, or passed to, a language model that can now generate an answer based on the entire prompt. So this is a system that we have created in order to make planprat. And planprat, planprat can be translated directly to the plan talker. It doesn't really translate well. But this is a chatbot that can answer questions about the content of zonal plans for a property. So what is the correct system message to give to planprat so that it will do its task correctly? Well, we can tell it that you're an expert at interpreting zonal plans and will assist residents in determining what is permitted on a given property based on the regulations provided in the planning data you are given. And then it needs to know that the relevant information from the zonal plans are the chunks of text. So we add the chunks from the search into the instructions. And of course, ask it to answer the following question and then add the question from the user.
All right, thank you. So let's talk a little bit about this pre-processing that Mathilde mentioned. So the pre-processing has kind of two goals. The first one is to get a textual representation of the plans, and the second one is to split them into chunks. And as we saw on Mathilde's slide, it is this part that we're covering right now. So we also want to kind of make the text somewhat standardized, but it's quite difficult because there's different images, there's different figures, there's handwritten text, and so on. And all of these plans, the municipalities write them in different ways because they can and they want to. Yeah, so there's a lot of different formats going around out there. So to showcase this, how it is to work with these plans, I ask all of you to close your eyes. Close your eyes. And don't open them before I tell you to. I can't see if you actually closed them, but I think most of you have closed them. Okay. Now, I assume most of you are developers, so pretend that you're walking into the office on a good day. If you're a PowerPoint warrior or something else, just imagine that you're a developer. So you get into the office, you're ready for a good day at work. During the day, you know, you attend some meeting, you spill out your opinions on a couple of matters. Mostly on which coffee machine's the best, or who in upper management would win a fight to the death, theoretically, of course. And you might even code a bit too. Now imagine the team lead comes in and says, you gotta parse some tables in the zonal plans. You think to yourself, cool, that should be an easy task. You're even gonna go the extra mile on this one and make sure that your code can parse any table. No matter how many rows or columns there are in the table, your code will parse it. Surely this should be no problem. So you get into a zonal plan and you find a table. Easiest table of my life. Now you can open your eyes and this is the table you find. And wow, it's actually easy. It's so easy, your code works flawlessly, but then you want to move on to another table. And then you see this one, and you're a little bit like, oh, wait a second. the top left corners, the cell is cut in half. What is going on here? And then you look a little bit closer and you find that there's not 2 headline rows. No, there's not 1 headline row. There's actually 2. So you have to make some adjustments, you know, but you get there, you know, and now you're all happy again. But then you see this one. And here you have, at the beginning, you have 2 columns. But then one of the columns, they split into 6 columns. And then there's visual representation. There's yellow and there's red. And there's probably way more information in one cell that could be split into multiple cells, and so on. And then you go, you traverse further, and you go into this one. You see this one, and here you have some weird maximum minimum stuff going on, but it's not in all of the cells, only in some of them, because it would be too easy if there was all of the cells that had maximum minimum in them. And then you see this one. And you're like, here there's multiple columns within one column, and I'm not even going to talk about this one, but then the AI team's personal favorite is this one, where you have multiple rows, or 2 rows in one row, and you have red and green dots, and how you're going to parse them, you have no idea. So yeah, that's how it is to work with these plants. So an inside and day of our lives. Yes, okay. But jokes aside, this story is of course a little bit exaggerated, not much, but a little bit. And how can you solve these problems? Well, one way you can solve it is to simply just give up. And if you detect a table, or if you need some information from a table, you can just ask the user themselves to go in and figure out what it says, because we have no idea. Or we could also try to use an LLM with vision capabilities. This one is a little bit unknown. We haven't tried it, but it could work. But if we as humans can't read it, it's also not that probable that an LLM could read it either. Okay, so a part of this pre-processing, we also stumble across a bunch of scanned documents. And what's so different about these is that scanned documents, you can't programmatically get the text from them. So you have to somehow use a different OCR model. And when you use one of these OCR models, it actually works quite well if the scanned documents are easy to read and well structured. Such as this one, we have on the top half, we have a scanned document, and then when you use some OCR, you know, everything gets out correctly at the bottom half here. But not all of the plans are that well structured, you know. Well, some plans looks maybe like this, where you have handwritten texts as well as at the bottom 2 lines here, you have some fields that are not filled out. And if you just perform OCR from this, well, first of all, the handwritten text gets incorrectly labeled, but also if you just get the text from the 2 bottom lines, it actually looks like it is approved in the building council and the municipality. As we can see, if you see at the bottom 2 lines in the extracted text. So how can we solve this? Well, if you use an LLM, a multimodal LLM, or an LLM with vision capabilities, we can now prompt it. So we can now tell the LLM that if you see some fields that are not filled, you could annotate it with, well, field not filled, or something like that. And if you do that, you actually get surprisingly good results. First of all, the handwritten text is almost 100% correct. But also, as we can see now, it actually says field not filled at the bottom. And now we also can understand that it is actually not approved anywhere, because there is a date missing. And then a funny one, you know, you will be surprised of the quality of these plants, but some of the plants look like this. And but even though that we barely can read them, the language models can actually read them quite well. This is all correct except for the middle part where it says vedtekter, and we think that the reason for that it can't read that is that there's too much gap between the letters in that word. But everything else is correct. All right.
Okay, so now that we've done some more processing, Planprat is able to analyze most of the documents. So what we did was that we implemented Planprat into a system called e-byggesøk, an application that a lot of architects use to fill out their building applications and send them to the municipality. And if someone reacts to broken English, it's because I used the automatic translate button in Google Chrome. This is, of course, a Norwegian website. So you can create your application, and the application is connected to a property. And you can now go to the Plan tab, and this is where Planprat lives. And now, since we know what property the user wants information from, we can actually use that to make Planprat better. So the first thing we do is to first fetch the relevant zonal plans, because we don't want to start searching for chunks of text independent of the zonal plans that are actually valid for this property. So we need to first figure out what zonal plans exist, and then we can do the rest. But now we can actually start prompting Planprat, ask it some questions. For example, how much can I build? And the first thing that happens is that it starts searching through the documents. So here you can see that it says which documents or which zonal plans it is searching in. So these are the zonal plans that are valid for this property. And it also says that it's searching in long and difficult documents, hold on, because this does take a while. The search part is pretty fast, but then waiting for the LLM to read the different chunks of data, the complete prompt, and then generate an answer, it takes some time, maybe around a minute. But if you're patient, you will get a response. And this is a much better response than having to read all of those documents. So now the system has been able to extract chunks of text and read it and then rephrase that text into an answer that actually tells us something about what the zonal plan says about how much you can build on that property. But yes, there's always a but.
There's always a but. So how can we tell if the answer here is correct, right? Because this answer, it could just be hallucinations from the language model. So we have a couple of problems, right? That's one of the problems is hallucinations, and that we can't double check this fact so easily because it doesn't say which plan the information is coming from or where in the plan the information is coming from. And furthermore, it also makes us able to actually potentially miss some important information. Because if we just take, for instance, the top 30 chunks for these three plans, we might end up with a skewed chunk set, if you can call it that. You know, so let's say that the first plan, or plan 1, it gives back 27 chunks, and plan 2 gives back 3 chunks, but then we don't get any chunks from plan 3. But and that's a problem, right? Because there might be some very important information, maybe not a lot, but just some information in plan 3 that's really important, and we don't want to make the same mistake as Permit Penny, who missed some important information in one of the plans. So we actually don't want to find the most semantically correct chunks, but we want to find the most semantically correct chunks for each plan. So we can ask each of the plans the same question, and then we get the top results from each of those chunks. So for instance, and then we can kind of tune it so that we know that we have information from all of the plans. So for instance, we could have, if we ask each of the plan, we can pick 15 chunks from plan 1, 10 chunks from plan 2, and 5 chunks from plan 3. And the way we do this, if you remember this one, Mathilde showed it earlier, is that instead of doing one search for all of the plans, we're doing a search for each of the plans. So here, for instance, we have 2 plans, and that means that we're doing 2 searches, which means that we're getting 2 different contexts. That propagates into that we get 2 different prompts, and these 2 prompts we can ask 2 different instances of a language model. And then, of course, we are getting 2 different answers back. These 2 answers can then be shown in the front end, such as here. We have asked the question, and then we get a response, and it says the kommuneplans arealdel, or plan 1, is saying this, while the plan 2 is saying something else. And now we can kind of easier double check and make sure that the correction, that the information is correct, and that the model is not hallucinating. Okay, but we can also kind of end up in an awkward situation here, because now that we search each of the plan, if the LLM is not able to answer the question, you're just going to have multiple times that, oh, I'm sorry, I can't answer your question. So we have some kind of detection on that if the LLM is not using any information from any of the plans, we ask the LLM a backup question if you can say anything about the question in general. And then it ends up that we only get 1 answer instead of listing multiple answers where the LLM can't answer. And the way we do this is by prompting. So the prompt here is, first you need to answer the question, and then you must indicate whether the answer comes from the attached zonal plan or not. And the entry you provide should always be in valid JSON format with 2 keys. The first key is content from plan, while the second one is answer. And then you have the JSON schema. Don't have to look too much into that, but basically we have a boolean, is content from plan, and if the LLM fills that out with false, then we can just throw away that answer. Then we know that the answer is not actually from a plan, and we don't have to show it to the user. And if all of the answers are false on this boolean, then we can ask the backup question. So let's take a look and look a little bit closer on one of these answers. So now we have an answer for each plan, but it still really still references a lot general areas, such as it depends on what part of the municipality you're in, or general living areas, or special living areas, or a field called B1 here and another field called B2. So it doesn't really know where in the plan it is situated.
Okay, so we need some more geospatial information. So just to be clear, in the documents, there are references to areas. And the areas are just given a name, for example, B1. And these areas can be seen in the map in the zonal plan. So in order to understand how the rules affect different areas, you need to both read the document as well as look at the map. And we ideally don't want the user to have to do neither of those 2. So we know what property we want to fetch information about. So we can use the property border. And similar to when we did the intersection analysis to find which zonal plans exist for the property, we can now actually check what parts of each of the zonal plans are intersecting the property, so that we can get a list of which areas are actually relevant to this specific property. And this information can then be fed into the LLM. We can't really just filter the rest out. We have to ask the LLM to do that task for us. So we just give it a JSON structure representation of the different areas that intersect with the property. And we give it some instructions for how to read this data. So we tell it that the following metadata describes which fields, areas, and zones the property falls within, and other fields and areas are therefore not relevant. So let's see how this affects the results. So if we go back to Planprat and ask it again, how high can I build? We now actually get a very concise answer. So now, instead of getting all of these references to the different areas in the zonal plan, we get a specific answer specific to that property. And it's way more, it's way easier to understand. So this was the first version. A lot of text, not that easy to read, and then with the geospatial information, it gets a lot better. Okay.
All right. So now that we've gotten this far, it's time to evaluate this system. And how can you do that? Well, in this pipeline, there's kind of two areas we want to evaluate. And the first one is the AI search. We want to evaluate if we are actually getting the correct chunks that we want to be getting. And the second part is the answer. Is the LLM actually answering correctly? So in order to do this, we need to create some kind of data set, a test data set. And in this data set, we need example questions. We need to know which part of the text is relevant in order to answer that question. And we need the ground truth for that question. And what we did is that we took some typical questions from architects, and then we added those. It's about 17 questions, but then you can ask those questions for a bunch of different plans. And we got help from some of the municipalities to help us answer these. And we did that by setting up some sessions, and they're experts. So they helped us fill it out in these sessions. And we end up with a kind of a data set in Google Sheets. Quite simple stuff. So some part of the test set looks like this. You know, you have a plan. You have the field, the BBB1, for instance. You have a question. You have the ground truth to that question. And you have all the relevant text that you need to know in order to answer that question. So for evaluation, we are using something called RAGAS. And it is an open source framework for evaluating RAG pipelines. It's using LLMs under the hood. So you have to take the results with a little bit of grain of salt, but it correlates quite well with what we're thinking we're doing right and wrong. And as a big coincidence, there are, of course, metrics for both the AI search we want to test and the LLM generation, answer generation. So RAGAS, they kind of calculate a bunch of different metrics, but we're going to focus on 4 today. The 2 first ones are only measuring how good the AI search is performing, and it's called context precision and context recall. If you're familiar with precision and recall from before, you're going to have an easier time on this next section. Then we have faithfulness, and that is only a metric for how well the LLM generates its answer. And then there is the answer correctness, which tests the whole pipeline in one go. So let's try to explain some of these. So the context precision, it basically is a measurement of how relevant the items are at the top chunks. And all of these metrics, by the way, they are scores from 0 to 1, where 1 is perfect and 0 is really bad. So that's quite easy to measure, you think, because you get the chunks from a search and then you just see if they're relevant or not. But how do you know if they're relevant? Well, you of course ask a language model. It's usually quite good, actually. Performs pretty well. Then there's context recall. And it measures if the content in chunks aligns with the ground truth. You can think of it a little bit as if the context recall is really bad, it's actually impossible to answer the question because you don't have the data that's necessary. The way it works is that it uses an LLM to make statements from the ground truth. So the ground truth can be multiple sentences, and the LLM then generates statements from this. And then it checks if the statements are then present in the chunks that you have received. And if it's not present in the chunks you have received, then it is, of course, impossible to answer. Then you have faithfulness. This only tests the LLM answer generation. And basically, it's just a way of measuring, is the LLM hallucinating or not? And the way it does it is that it takes statements from the answer generated and checks if it's present in the context. Because if some statements in the generated answer are not in the context, that means that the LLM is just making them up. Because where else are they coming from? And then you have the last one that goes through the whole pipeline, and that's answer correctness. This one is a little bit more technical to explain, but if you are a data scientist, you will maybe follow along. The way it works is that it uses an LLM to find the true positives, the false positives, and the false negatives, and then it calculates the F1 score for the ground truth. And then it takes the ground truth and the generated answer, and it finds the cosine similarity, or just how similar are these, and then it takes a weighted average of all of this. And it is a measurement of the whole pipeline. Don't think I'm going to try to explain that anymore. So let's look at some results from our model here. So here on each row we have we have all the metrics, and then in the columns we have 3 different experiments. So the first experiment, it just pastes the entire plan, and it acts like in one chunk there's the entire plan. The second one is actually using search and just takes the top chunk from the search. And the third one is taking the top 10 chunks from the search. So if we look here, we can see the context recall is really high. That makes a lot of sense, because if this would not be really high, then it wouldn't be able to answer the question at all. So the entire plan is doing really well. If you only choose one chunk from the search, we can see that's way too little information. If you only use this, it is actually not possible to answer the question. But you can see at 10 chunks, the number goes up again, and you can kind of see that it's not as good as the entire plan, but it's almost as good. Then we have context precision. It says something about if the top chunks are relevant or not. And since the entire plan and the one chunk from search, they are just retrieving like kind of one chunk, we can see that the LLM deems the entire plan kind of relevant. You would maybe think that that number would be a little bit higher, not 0.769. But the reason for that is that when you paste the entire plan, you get all the relevant information, but you also get a bunch of other stuff that is not relevant. So then the score goes a little bit down. And then you can see from when using search, it is not really good enough, and that the search here is probably not doing a good enough job. As we can see, the scores are actually quite a lot lower. Then we have faithfulness. This scores pretty well across the board. It checks if the answer from the LLM is in the context, so it's measuring the hallucinations. So when you paste the entire plan, there's actually not that much hallucinating, and we can, for the most part, trust what the LLM is saying. But we can also see that if you only use one chunk from search, the LLM then gets a little bit insecure, or what you can say, and then it might start saying stuff that is not from the context, and we do not really want that. And then it gets a little bit better again if you take the top 10 chunks. And then we can see the answer correctness, which is measuring the whole pipeline. And you can notice here that for all of these, there's a big drop in performance. And you can see that the entire plan is performing best. But the reason for this big drop is that the LLMs, they are quite verbose. They really like to talk a lot. And in the AI team, we have deemed it or called it bot-splaining, because the bot is just rambling on. So usually, actually, the bot or the LLM is pretty good in the first couple of sentences to get the correct answer, but then it just keeps rambling about some semi-relevant stuff, and since that's not good enough when measuring onto the ground truth, then the score falls. So here we have some probably some prompting to do to make the LLM answer more concisely. Yes. So also a big thing to think about here is that these numbers doesn't actually really tell us if we're correct or not. But what it does allow us to do is that we can tweak a lot of parameters, and then we can say if we're doing better or worse after those are tweaked. And there's so many things you can tweak here. You can change out the search algorithms for the AI search. You can tweak the search parameters within an algorithm. You can change the chunk size. You can change the rules how to split the chunks. Should you split them on paragraphs or should you just split them by characters? You can change the LLMs and see if one LLM performs better or worse than another one. You can change the parameters within an LLM, temperature, top P, top K, and that kind of stuff. And then you can, of course, change the prompt, and that is just an infinite amount of work. You can do zero-shot prompting. You can do few-shot prompting. You can try chain of thought. You can try React. All these kind of things you can try and tweak. So yeah, all right.
Okay, so now that we're able to actually evaluate our system and tweak all of these things that Malte just said, one of the obvious things to test are different models, both due to performance but also cost. So first, what models are we using? To generate text, we use GPT-4 Turbo from Azure OpenAI, which allows us to have the models hosted in Europe, which is very nice security-wise. And for the search, we use Azure AI Search with the embedding model called ADA. And these models are state-of-the-art models. They work really well. And most of you, or some of you, have probably heard about the new GPT-4o model. It's not available in Europe yet through Azure OpenAI, but we'll probably switch to that one when it's available. But yeah, these are state-of-the-art models. But they are trained by big American companies. So their main language is English. They know Norwegian. They're really good at generating Norwegian text and reading Norwegian text. But their main language is English. And how does this affect the performance? Let's look at the tokenizer for GPT-4. So the tokenizer is the first step when an LLM needs to read some text. Malte explained earlier. So when you paste some English text to a GPT-4 tokenizer, you can see that it splits the sentence almost word by word. If you translate this sentence into Norwegian and ask GPT-4 to tokenize that sentence, it looks very different. It splits the same word into 2 or maybe 3 tokens, and it doesn't make logical splits. There's one, like the age alone doesn't mean anything in Norwegian. So you can see that it performs, it's not as good in Norwegian as it is in English, and you also get a lot more tokens. And the more tokens you get, the more compute power you need to process the text, and the more it costs and the more time it takes. So what are our options? There are Norwegian LLMs available as well. There are lots of initiatives from different universities and so on. And one of the models that are trained on Norwegian is called Norbert. So we tested the Norbert tokenizer to see how it was different. And there is actually a huge difference. So when you use Norbert that is trained on Norwegian text, you can see that it tokenizes the text the same way GPT-4 tokenizes English. And if we paste the English version, you can see that it tokenizes the same way as GPT-4 did with the Norwegian text. So you can see that it actually makes a difference. So here you can see some of the benefits of working with a model trained on your specific language. But what about domain? Are there also gains to be made from having a domain-specific model. That's what we're testing with Planbert. So Planbert is our own embedding model, and it's a part of Henrik's PhD project. And he has taken the Norkart model and fine-tuned it on plan-specific data, data from zonal plans. So he has trained on 70,000 Norwegian zonal plans, which is a lot of text. But with these models, it's the more the better. So he wanted to produce even more text to use for training. So what he also did was that he created 150,000 synthetically generated questions. And the goal of this is to create even more data that also talks about the domain within the zonal plans. So how can you do this? Well, you can ask an LLM to generate those questions for you by looking at chunks of text from the zonal plans and ask it to create questions based on the content in those chunks. So let's look at the prompt. He has asked LLM to do this. Given the following instructions, generate a question that can be answered only by the following reference text. And then he has to specify that the model should answer in Norwegian. And the LLMs aren't always that good at taking instructions, so he also specifies, do not answer in English. And then some more tips: do not ask when documents were created or updated. That's not what we're interested in. Do not ask about the author of the text. And remove all unnecessary details. This is to avoid the bot-splaining that Malte mentioned, where the model just adds a lot of extra text. So by prompting this, you can then add a chunk of text from a zonal plan and get a question based on the content from that zonal plan. So here are some translated examples of synthetically created data. What must be approved before a building permit is granted? What type of roof is required for houses in residential area, B10, and so on. So you can see that these synthetically generated questions actually relate to zonal plans. So how does this work? This is very early work. He has only been working with this model for a couple of months. But so far, it looks promising. So we have two different data sets, and Planbert actually outperforms the ADA model on one of our data sets, and on the second one, it's pretty close. So the NDCG score, I won't go into detail on how it works, but 1 is the top score and 0 is the lowest. But the point here is that creating this embedding model with the text from the zonal plans and also having a Norwegian embedding model seems to be working better. Okay, so last we would just like to share a little bit about our tech stack. So everything is written in Python. We use Flask and Unicorn for our API. We use Docker, and both for hosting our system, but also for developing, with the dev containers in Visual Studio Code, which is very useful, especially when you want to test different LLMs and you need the different hardware. And we use Azure to host everything. And then lastly, we use a library called LangChain. And this is a Python library that is very popular when working with LLMs. It has a lot of tooling, and it makes it really easy to instantiate different types of LLMs, either an Azure OpenAI model or a model from Hugging Face. OK, so what now? Well, we're at the stage where we are continuously improving our system and using the evaluation system to figure out how we can tweak it so that it will get even better. And we are also in the phase of having pilot users. So we have 3 different architectural firms that are testing Planprat and seeing how it works. And we have also implemented a version of it into a different system that allows the municipalities to also test the system, to see how the system works for their zonal plans, and maybe they'll also realize that the crazy tables aren't such a good idea. We have also been talking a lot about different user faces, because does it have to be a chatbot? There are so many chatbots appearing everywhere now. Not everyone are fans of them, but there are different ways that we could have created the system. The chatbot is the first version, but we could have also extracted information that we know that the user most likely wants and then presented it in, for example, a table. But there are so many different ways that we can use a system like this to extract information from these documents that the user wants. So during development of this project, we have had a running joke that planprat is just a faster way to get the wrong answer. So if you read all of these documents, you're not going to get the right answer anyway. You're just going to end up like Penny, really frustrated. So now at least you can get the answer really fast. But of course, our mission is to create a system where we can say that planprat is a faster way to a complete and correct building application. Thanks for listening.